Hi, and welcome back. Today's lecture is going to be brought to you by Midnight, who is having a nice little nap in the middle of our class today. And today we are going to be talking about Chapter 11, Sections 1 and 2. The topic is derivatives of logs and exponential functions. A few things about this. Chapter 11 has a couple of other sections in it. We are only going to be covering section 11.1 and 11.2, and we'll be talking about that today in part 1 and part 2 of our lecture. Okay, so I want to remind you about a few things about log functions and exponential functions. In your finite math class or in your college algebra class, you probably spent some time on logs and exponential functions. You talked about maybe some of their properties, maybe solved some problems involving exponential functions and log functions. What we're going to be talking about is we want to talk about how logs and exponential functions relate to calculus. And in particular, we want to be talking about the derivative of a log function and an exponential function. So before we talk about those derivatives, I want to remind you of kind of the highlights of exponential and log functions. So you might remember that an exponential function is a function that looks like f of x equals e to the x, or maybe f of x equals a to the x. And the reason these guys are called exponential functions is because the x, which is your variable, is up in the exponent. The base of e is a number, and a is some other generic base. E is a really special number. It's 2.7 blah 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 blah. You can type it into your calculator. It's kind of like pi in the sense that the decimals go on forever and ever and ever. For some reason, it's not quite as hip and cool as pi, but anyway, e is the number that we're looking at here. Okay. We are mainly going to be focusing in terms of exponential functions on f of x equals e to the x, but you want to be aware that you can have other bases as well. Okay, so that's what an exponential function is. When we talk about a logarithmic function, we're talking about a function like f of x equals that's wrong. F of x equals natural log of x, and I can put the x in parentheses or not, it doesn't matter. Or I might have something like f of x is equal to log base a of x. So the one that we're going to be focusing on is this ln function. You read it as natural log, but it's ln because it's French, I think, which is log naturel or something like that. So this is the natural log of x, and this is a log base a of x. And the thing is that you might have talked a little bit about how to translate between exponential functions and log functions. And so we can translate between the two types of equations. So for example, if you have y equals log base a of x, this means the exact same thing as writing the base, which is a, raised to the y equals x. Okay. So the thing that's inside the parentheses is in the translation into an exponential equation is the thing that's over here on the right side, and the thing that was by itself is the exponent on the base, which that base is that subscript right there. Okay. All right, now if we're talking about y equals natural log of x, natural log, the thing that's special about that is that's actually log base e of x. And so when I write y equals natural log of x and I want to translate that into an equation that has an exponential in it, then what I write here is, okay, I have my base, which is e, raised to the y, that's the letter by itself, equals x, which is the thing inside the parentheses. Okay. All right, so that might look familiar. If it doesn't look super familiar to you, that's okay. We're not going to really see that too much. Okay. Maybe one last piece of information that I'll talk about in terms of properties, algebraic properties, is that if you have natural log of e to a power, that this is exactly the same as just the r. So when we talk about exponential and log functions, the thing that is cool about them is if we're talking about e to the x and natural log of x as a pair, they're actually inverses of each other and they undo each other, which is why when you apply a natural log function to e to a power, what it does is it erases the e and leaves you with just the power. So the natural log kind of undoes the exponential function. On the other hand, you can also write down e raised to the natural log of something, and now the e is sort of, in some sense, canceling the natural log and leaving you with just whatever we have the natural log of. So e to the natural log of a is just a. All right, so everything that's written up on the board right now is all sort of properties of logs and exponents. And if you're super excited about logs and exponents, you might go and Google some of these properties, or go back and look earlier in your textbook and see if you might want to remind yourself of some other properties. But these are the ones that at the most we will need for this course. All right, so let's talk about some calculus. So we want to focus on, for this class, the derivatives of these functions. And the thing about these functions is that they're nothing like any of the other functions that we have talked about. Like, we have a power rule for x raised to a number, and we have rules for if two functions are divided, the quotient rule. We have a derivative rule when two functions are multiplied, product rule, and things like that. But these functions, this natural log of x or maybe e to the x, they are totally different animals. So we are going to have two very different derivative rules that you have to memorize separate from all the other derivative rules we've learned. All right, so let's talk about, for this first part, part one, we're going to talk about the calculus for natural log. In part two, we'll talk about the calculus for the exponential function. All right, so you might remember what the natural log function looks like. If you don't, you can graph it on your calculator. But here's a picture of the natural log function. So the natural log function kind of starts really low on the y-axis and kind of pops up and then just kind of flattens out over here. And this graph crosses the x-axis at x equals 1. Okay. All right, so some things that you might notice about this particular function are, well, that function, the natural log function, never shows up on the left side of the graph. So if you tried to type in natural log of, say, a negative number, an x value over here, natural log of any negative number, and you type it into your calculator is either going to yell at you and tell you about some domain errors, or it's going to explode. So check it out and see what happens for you. In terms of calculus, in this class we're focusing on derivatives, and derivatives are talking about the steepness of a graph and the shape of a graph. So when is a graph going uphill? When a graph is going uphill or increasing, then its derivative is positive. When a graph goes downhill, its derivative is negative. So some observations that I can make here are that the function f of x equals natural log of x is an increasing function. And when our function is increasing, that means that its derivative, or the slope of the function, is positive. Okay. Another observation is that when I look at this shape, the shape of this graph, if I were to draw tangent lines on this graph, the graph would always be below those tangent lines, which means that this graph is a concave down graph. So f of x equals natural log of x is concave down. And what we talked about last time is that this concave down shape, this sort of upside down u or lowercase n shape, we talk about that as concave down, and concavity is determined by the second derivative. So when the second derivative is positive, the original graph is concave up. When the second derivative is negative, the original graph is concave down. So we have a concave down graph. That tells us that our second derivative is negative. Okay. All right, so these are observations about the natural log function. Okay. Second comment about this, there is log base A functions. You can read about those in the textbook. We are focusing strictly on the natural log function. So natural log has a base of e, and that's the one that we care about. Okay, so here is our new derivative rule. If f of x is equal to the natural log of x, then the derivative f prime of x is equal to 1 over x. Now you might say, well, Diane, how did you get that 1 over x from that natural log of x? Well, there's no method for how to get that. That just is the derivative of natural log of x. Now let's talk about why it might make sense, or why this is a legitimate choice for our derivative. Okay, so back over here on our graph, some things that I observe here are at the beginning of this graph, our graph is very steep. And here toward the end, if I were to extend this graph continues to increase, continues to go uphill, but gets flatter and flatter as we go along. So the beginning of our graph is very steep, and the right-hand side is flatter. So let's take a look at an example. So for example, let's say that I look at a really, really tiny number, like say x is equal to 0.01. So that's a really tiny number, okay? And that corresponds to a point that's way far down on this graph, really, really steep here, okay? When x is equal to 0.01, and this is just an example number, I've just picked it out of a hat, then f prime of 0.01, well, if I plug 0.01 into my derivative formula of 1 over x, I have 1 over 0.01. If I type that into my calculator, what I get is 100. Okay. All right, so my derivative is 100. That's the slope. That is a wicked steep slope. That says for every 1 unit to the right, the graph goes up by 100 units. Okay. All right, so very large slope. Okay. On the other hand, if I choose some really big x value, like x equals 500, let's say, so now here's 1, and 500, well, it's not really drawn to scale. 500 is probably like way over here, but that's okay. I'm going to put it right about here. So here's 500. If I go up to the graph over here, our graph is very flat. And so if I type in x equals 500 into my derivative formula, I should get a slope that's really small. Let's see what happens. When x is equal to 500, f prime of 500, our derivative is 1 over x, so f prime will be 1 over 500. And if you type 1 over 500 into your calculator, you're going to get 0.002. That is a tiny, tiny number. And is that 0.002 or 0.02? I guess that should be on your lecture notes. You should add an extra 0 in, because I just looked at mine and realized I typed it in wrong. But anyway, so this I think is the right number. You should double check that on your calculator. I don't have anyone here to second that. Midnight is here to second that, but she can't type it into her calculator because she doesn't have any opposable thumbs. Oh well. Okay, so the point is that for large values of x, our graph is very flat and has a small slope, such as 0.002. For very small x values, when we plug those into our derivative, we get a really big number, meaning our graph is very steep. So in that sense, this derivative kind of makes sense. Okay. As far as the second derivative goes, if our original function is natural log of x, then our first derivative is 1 over x, that's by our new rule. And then to calculate the second derivative, well, if I want to look at the second derivative, I need to take the derivative of 1 over x. One option is the quotient rule. That's kind of a pain. I can rewrite this as x to the negative 1 and take its derivative. So our derivative will be negative 1 x to the negative 2. Okay. All right, so as an example, let's say we look at when x is equal to 2. So here's 2 on our graph, and here's our point. Okay. This graph is concave down. When I plug in x equal to 2 in my second derivative, I'd better get a negative number, because when our graph is concave down, the second derivative should be negative. Let's see what happens. When x is equal to 2, our second derivative, plugging in x equal to 2, gives us negative 1 times 2 to the negative 2. All right. You should type this into your graphing calculator and see what you get. Double check that, and I did this ahead of time, double check that you get negative 0.25. Second derivative is negative, tells us our graph is concave down, which it is. Okay, we're going to take a time out. Don't stop yet. Wait. We're going to take a time out, and we'll come back and do some examples of calculating derivatives with our new derivative rule.